So our project idea is IoT-based solution for recording and storing metrics of normal and orthotic leg for analysis by Orthotist. Our team members consist of myself, Piyush Gupta, Baliraja Nemade, and Vedant Raut. We are from Vidyalanka Institute of Technology, Mumbai. So here, basically, we are doing is that we are finding the efficiency of the assistive device, which is wear by the orthotic patient. So it's an IoT-based solution which would record and store the metrics of normal and orthotic leg for the analysis of the orthotist. So our main objective is to measure the gait parameters of the leg, and then those parameters would be compared with the normal leg, and after that a quantitative report will be generated, which would assist the doctors as well as patient um, to improve their gait by suggesting certain exercises or medication to the patient. Before we started our project, we did few surveys across the Mumbai, and we got to know that there is only one functional gait lab, which is in Jupiter Hospital, Mumbai. So Mumbai, like a metropolitan city, have only one gate lab, which which creates a huge burden on the lab. So from this survey, we also got to know that there is two methods to calculate to measure the gait parameter of a patient. So first is the manual method where the doctor just observe from the bare eye and then and conclude what is the problem with that patient. Uh, as this type of technique is very fast, but the problem with this type of system is that doctor cannot don't get any metric data to validate uh, his uh, his observation. And the second method is the motion capture system. This type of system is very advanced as high definition IR cameras and then many other devices. This type of system gives very high reliable data, but the problem with this system is that it takes very long period of time to generate a single report. Due to this disadvantage, doctor have to drop certain type of patients. So to solve this problem, we have came with an camera-less system, which would be a cost-effective and variable and easy to set up device. Here basically the patient have to wear the device and walk. So right now we are focusing on two type of data. First is the orientation data, and the second is the pressure data. And the data will get collected by the microcontroller system, and it would be stored in a cloud storage. So further, the hardware part will be explained by our team member Baliraja Nemade.
So for the pressure, we came up with this solution. We made our own pressure sensor, which uses a pressure sensitive material, velostat, which is sandwiched between two copper films, which uh, gives us a sensor. So so the sensor is placed on four weight bearing points, which we found from our research, and putting pressure on one of these gives us the a pressure result. This is also used to find the gait phases of the patient. Next parameter to calculate is the orientation. So, so the orientation is divided into two parts. First is the flexion and extension part. For for each flexion and extension, we are using two IMU sensors. So let's see if we have to find flexion extension of the knee, we are using IMU2 and IMU3 to find this angle. So each angle will give us three parameters in X, Y, and Z, and we are calculating four angles for each leg. Next comes the foot progression angle. For this, we are using an IMU sensor which is placed on the top of the foot. So it gives us the deviation of the toe from the central axis. And we are using the accelerometer and gyroscope for this and formulating in this way. So from the insole that we have created, we are using it to find gate phases. So and this comes from simple fuzzy logic. So there are six cases of gate phases. So so it is simple. The part which gets pressure on is represented as 1, and which doesn't get pressure on, it's represented as 0. So we have arranged this and we found six cases, and this is how it is divided into that. So this is how we are determining the gate phases. This is important because we can differentiate at which particular point or which phase the person has a problem. The next parameter comes is the average gate velocity. We are calculating average gate velocity per gate cycle, and it is determined from the total distance and time taken for each gate phase. The rest of the parameters are as follows. Cadence, a double support time, stride length, step time. We are using these formally to find out these parameters.
Now coming to the IoT model, uh, our model is divided into 5 parts. So first one is hardware implementation. It involves the acquisition of data from the sensors, which are IMU sensors for the orientation and pressure for the pressure sensors for measuring the pressures. And with the help of a microcontroller and a Wi-Fi module, we are sending our data to a real-time database server. And that data from that database server, we are divided into three parts. A data pool of three parts: pressure, orientation, and gate speed. And through our machine learning algorithms, we are predicting the corrective measures, and that we are involving in our report. And that report is we will send it to a patient via email. Next. Coming to software implementation, our software implementation is divided into four parts. First one is recording the data at the sample frequency of 35 hertz from our sensors, and storing it in a flash storage and sending it to a real-time database server for global accessibility. And second part involves organization of data. So these are the ways we are organizing our data. Now coming to the analysis of our data. So as you can see from the example image, uh, we are isolating one gate cycle uh, 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 on our x-axis, and on y-axis we are plotting it with angle. So brown and blue line indicates left and right leg respectively, and that shaded portion uh, is the normal leg data, gray region. And if our data lies within that portion of gray, then we can say that they are normal. And if it is anything beyond that, then we can say it is abnormal behavior of that gate phase. So we can pinpoint to the a location from our x-axis where exactly problem lies. So from the given data, ML model will develop conclusion and provide corrective measures. It will also calculate the efficiency of device at each parameter. Now sending data to the orthotist. So we will acquire all the patient data like his height, gender, weight, etc., etc., and include it in our report. And we will include the graphical comparisons, analysis, and suggestions taken from the machine learning model, and conclusion made by the orthotist and review. And then we'll send it to the patient via email. And here is our technology stack, as you can see. And now coming to the competitive analysis, we have performed this analysis by comparing it to an industrial solution, which is the marker-based mocap system. We did a survey at Jupiter Hospital and compared our device with it. So first point, preparation time. So from what we have understood from our survey is that it requires quite a lot of time for just the placement of the marker in industrial solution, that is the mocap system, and whereas our solution only requires 5 minutes for wearing the device. So it is fast in that regard. And coming to the post processing, the mocap systems actually require a technician to assess the machine for post processing, and whereas our solution does that automatically. And coming to the post processing time, that mocap system actually requires around the industrial solution requires around 2 to 3 hours, whereas our solution does the similar analysis in 10 minutes. So, and possible side effects, coming to the possible side effects, uh, mocaps, that marker based mocap system requires a glue to be sticked on your skin, so it can cause skin irritations uh, and can have unnatural movement, and marker can drop, whereas our solution has no side effects. And coming to the portability, as you must have seen in that gate lab, it is quite a huge setup, so it is not portable and cannot be used wherever we want. It requires special conditions to be satisfied to be used. So in that regards, our solution is portable and can be used almost anywhere. And coming to the maintenance cost, uh, the marker-based mocap system requires a high frame video cameras, also large space, and it has a very high maintenance cost. whereas our solution has a very low maintenance cost. From what we have uh, understood from, we have concluded that is that uh, our solution helps a lot of people with leg disabilities who have been struggling to be treated due to inefficiency of state of the art technology. uh, our mobile lab offers various opportunities for patient care, and it also helps in personalizing the treatment protocols for surgeons in planning surgery, and and it is also faster, more cost effective, and very reliable compared to the market competition. Next. So coming, this is our prototype. As you can see, uh, it on the patient's leg. The highlighted part is an IMU sensor, which is used to find one of the IMU sensors, which is used to find the orientation, and the highlighted part indicates the microcontroller unit, uh, and this is our pressure insole, which is placed under the foot for pressure mapping. And on the right side, you can see our software for gait analysis. So now we will demonstrate our prototype.
So this is our hardware part. As you can see that we have applied our device on patient. He has some ankle problem. In this case, the patient has to walk for around 10 seconds for the data to get recorded, and the recorded data is sent to the cloud server. These are the indications. Blinking green LED means that the device is calibrating itself. Bright red means Wi-Fi is connected. When the blinking stops, it means it's time to go. And when it's done, green LED is turned off and red LED starts blinking. It means data is being transferred to cloud. When red LED is off, it means data upload is complete. Now we are on the orthotist side, the doctor's side. So the doctors responsible for the patients will have access to this software which we have developed. This software will acquire the data which has been sent by the patient through our device to the cloud storage. And this device and this software will be used for analysis purpose. So here is the first step. It's just basic details. For a testing purpose, we have named the patient as patient, and his age was 6 and I was 32 and he was 8. This diagnosis part is optional, but since we have it, we can input something. So it will help even more. So now we will fetch the data. So the data is set by the name of the patient. So here we have the data. These are the records in here. So let's select the first data and then we will download this data. The downloaded data will be converted by the software into graphical format. So we can view graphs for each angle and for pressure too. We can fairly conclude that this patient has some problem with his right leg. And so after analyzing these graphs, orthotist can put some remark. So maybe some remark. Yeah. Then we will generate a report. This report can be sent to the patient through mail or contact number if it is linked to any media. So for testing purpose, I will send it myself. So we'll click on the send email and it will send the email to my inbox. Yeah. And it has the report attached to it. So let's open the report and see how it is. So the details that we have mentioned are here and the graphs are incorporated here. So, and the best part about this software is that it can use machine learning algorithms to sort based on the graphs data to provide some measures from this database. It's entirely based on the database. So the more data we have, the more we can conclude something. So this analysis part is based on the software which it has generated from the database which we have provided it. So next part is the tempospatial parameters which we have gotten here, supplying step time, etc. The units and the orthotist remark which or the orthotist will be putting in the software based on it. So this is the whole procedure of our project of our idea. So we are thoroughly aiming to increase the reach our for a product so that many people can be diagnosed even faster, less time, and it can be reached to any corners of the world. So this is our work so far. Thank you for listening.